So let's say I put in a 0 and a 1 and a 2. I don't know. Let's see. So if I put in a 0, I just get -2. If I put in a 1, I have -3 minus 2. That's -5. If I put in a 2, I have -6 minus 2. That's -8. So let's see. 0, -2 is there. 1, -5, 1, 2, 3, 4, 5. And I'm not going to be able to plot this dot because it's down here, so it's going to be hard to be accurate. So I'm going to put in a -1 for x. Let's see, that'll give me +3 minus 2, right? Because in that case, I'm doing -3 times -1 minus 2, so that's +3 minus 2, or 1. Okay, that dot I can plot. That's 3. For accuracy, it never hurts if you have time. Say you're taking a test and you're finished early, it never hurts to plot more points. Sometimes you catch mistakes that way. So let's see, if I put a -2 in here, I have +6 minus 2, that's 4. So I'm going to plot the point -2, 4. So 1, 2 to the left, and 1, 2, 3, 4 up. Okay, and then ideally, I don't have a straight edge with me here in the studio, but ideally you're going to use a ruler to make a nice, neat straight line. Okay, and so hopefully that's what your line looks like. Now, notice that in both of the above problems, both the example I did for you and the Build Your Understanding problems, when you connected the dots, we obtained a straight line. And I even mentioned that the graph would be a line when I was talking about it. Now, how did I know the graph was going to be a straight line? Well, I knew this was the type of equation. So equation whose graphs are straight lines are called linear equations. Now, an equation is linear. You can tell it's linear, and this is how I knew the graph was going to be a straight line, which, by the way, is a very helpful thing to know. An equation is a linear equation, so straight line graph, if it can be put into the form ax plus by equals c, where these capital letters are representing constants. In other words, they're just numbers that you'll see in the equation. So the x and the y, you'll see actual x and y's. They'll be variables, but you won't see a, b, and c. You'll see numbers there. So, for example, that one that you just graphed, y equals minus 3x minus 2, if I add a 3x to both sides, I would get the equivalent equation, 3x plus y equals -2. Okay, so this is in that form. Number times x plus number times y, because there's an invisible 1 coefficient there, right? So number times x plus number times y equals number. Okay, that's what we mean by saying we can put it into that form. Now, what was I going to say? I don't remember. But anyway, this form is known as standard form. Oh, yeah, I remember what I was going to say. Just a quick way of telling that an equation is linear without trying to put it in the standard form or looking at the standard form. Notice that the x and y's don't have powers on them other than the invisible 1 exponent. They're not inside square roots. So that's the quick way of telling that you have a linear equation. And maybe we should make a note of that. So no exponents on the x and y. They are not inside any kind of radical like square roots. Also, when I say they, I mean x and y. Maybe I should write that, x and y, just to make it clear in your notes. Also, x and y are not in a denominator. Okay, so there's nothing happening to the x and y except that they have numbers multiplying them, and they're being added and subtracted. Okay, that's the type of equation that's linear. So you can pretty much tell it at a glance because it's again, because there's nothing happening to the x and y other than they're being multiplied by numbers, and then there's addition and subtractions going on. Okay, so that's standard form. Now, not all equations are linear, as the following examples will show. And I'll just go ahead and do a couple of examples for you before I turn you loose on some nonlinear equation graphing. Oh, and let me just mention one other thing before we go on to nonlinear equations. So remember what I said about the graph being a picture of the solution set? Well, we use our XY table to find a finite number of solutions. So each of these dots is an XY ordered pair solution, right? So, for example, this one, what was that? That was 1, -5 is a solution to y equals minus 3x minus 2, right? You can check that if you want to, and that's not a bad thing to do. If I put a -5 in, is that equal to what I get putting a 1 in for x? Well, that would be -3 minus 2. Yeah, so that checks out. So this ordered pair, if I put it into the equation, gives a true equation, so it is a solution. Similarly, all the three other dots that I put in are solutions. So the dots represent particular solutions to the equation, and it turns out that, remember I said there's infinitely many solutions, and you can see that I could keep going with my XY table, but there's no point in keeping on and on and on and on, because you can never find all the solutions, right? Because there's infinitely many of them. And dots in between, even if you found infinitely many dots, the dots in between the dots you found are also solutions. So what we do is we make a finite number of dots and connect them, and then the graph, this is called the graph, when you find some solutions, connect the dots, that graph is a picture of the solution set. So every dot on the graph is a solution, even though they have weird coordinates that would be hard to come up with. But they're all solutions to this equation, and contrariwise, it doesn't matter. Anyways, similarly, on the other hand, let's say on the other hand, I just said every dot on here is a solution to that. Similarly, every solution to this can be found as a dot on this line.